Okay, let's get started. So correction. So where was the correction? What am I talking about? Okay. I think the correction I need to make is that I totally forgot how to make a correction. Yeah. So one thing. Oh yeah. One thing. The last time I talked about gamma metrics for Ramon. So one mistake is this one. And this, and so this is clipboard algebra. I introduced for Ramon zero mode. And then I define some raising and lowering operator. And then this part I made a slight mistake. So it was like this way, but this is not true. I think this is plus minus. And then this week's homework, you need to consider this week's homework spin representation or Dirac and the while, and then Majorana condition and so on. Essentially, it's a reading assignment of the Poczynski Appendix B. Poczynski's book is not that easy to read. But Appendix B is very nice. It's a kind of must read. So you should read. And also today we will use a lot of representation theory of the spinor representation, or in general, like spinor representation. Appendix D. So that's this week's homework. And thanks for pointing out my mistake. So G constant term is something like what's the R squared minus 4 C over something delta R plus S 0. So this should be 1 over 4 quarter. So this is the homework mistake I made. Yes. And yeah. So that's the correction I need to make. Yeah. Okay, so that's the correction I wanted to make. What else I want to make the correction? Hopefully it's okay. Okay. Yeah, I think now it should be okay. So the last time, and also, oh yeah, and so the calculation A ghost, I did a strange explanation of 15 over 45, 24, and minus 15 over 24. 12 minus 1 over 12 and minus 5 over 8 is Ramon, and S should be something like minus 1 over 12 plus 1 over 24 is equal 1 over 1 half. Okay, yeah, this. And this one coming from central charge. This is coming from central charge. And this one comes from normal ordering. Huh? Oh, this one plus here. This one plus. Okay. Ordering. Okay, good. Thank you very much. So there was typo. Okay. Did I correct it? Did I correct in lecture note? Sorry. So I just printed out a week ago. I didn't correct it. I use old notes, so that's why. And this 12 plus sign comes from really the what was it? The stress energy tensor of the BC goes. I will make a lot of mistakes. You should point me out, as you already noticed. What was the stress energy tensor for BC ghost? Stress energy tensor BC ghost L0 is indeed sum of minus n, and I have to b minus n. Is this correct? And rounds for z. Is this correct? Let me write it down. So L0 is equal to sum over minus n, and then I don't know the correct ordering here. What was the? I think I have written down correctly in somewhere in homework or any lecture note, which I don't have it now. So let me check now. So, okay, so this is correct. So Bn and C minus n. So this is correct. L0, and then plus some normal ordering constant, minus 1 as far as I remember. Yeah, minus 1. Okay. And this 1 over 12 really come from normal ordering coming from minus n. So this 12 plus 12 is coming from sum over minus n over n equals to n is greater than 1. The normal ordering coming from this minus n, minus sign, this plus sign coming from this minus n L0. So that's the reason you get the plus sign here. So that's the correction I need to make last time. Okay. Okay, so today we are going to talk about this spinor representation. And this week's homework is also spinor representation. And the Appendix B of Porchinski is very, very well written, and they often physicists has to deal with fermions. So to fermion, and the fermion is indeed spinor representation of spin group. So you have to be fluent about the spinor representation. So Appendix B is kind of must read for physicists. Here, usually in QED, you start with whatever, QED or QCD. I mean, you have F mu minus 1 over 2 or 4, anyway, plus psi d slash psi, and or maybe minus I times. And then you have a gamma matrix gamma 5. Gamma, there's some number times gamma 1, gamma 2, 3, and so on. Then you have critical algebra. That's what you learn in QED. That's what you learn in QED. And then the psi can be written in the positive and negative chiral spin. ball spinner. That's what you're learning 4-dimensional. In the Polchinski appendix, it's a general dimension. So, and then in the homework, I asked to do like any even dimension, but there is some periodicity up to mod 8. And we will use the representation in today's lecture. Okay, let me recall last time. So if you define this plus minus, okay, plus minus this creation, creating a lowering operator, they satisfy. Let me recall a little bit. Delta ij, otherwise 0. Otherwise, this gamma plus plus is 0, gamma minus is 0. And then, and also, okay, let me move on. So then you can just have 2 to the 5. So this is something like a raising. You can consider raising, and this one can be understood lowering operator in fermionic sense. And you can have a Ramon ground state can be understood as S0, S1, S2, S4, and the momentum, and then S, we call it K, and then SI is either plus minus or down. So in Ramon ground state, naively, without imposing any like a quantization condition or physical BRC quantization condition, it's just 2 to the 5, which is 32 states. And that is creation, raising and lowering operator really, swap the spin down and up. That's what. Okay, and then, so this 32 is decomposed 16 plus 16 prime. Okay, so in general, people just, there is 2 ways to write that. So in physicists, when you say irreducible or representation, you just write down the bold number, like a bold number to say, to specify representation. Or physicists, people just sometimes write down the, underline. So since now the number is big, I will use underline to specify representation. And again, this gamma is 16, and the 16 is really 11. So it's corresponding this chirality operator. Corresponding chirality operator that is defined by some number times 2 to the 5, as far as I remember, 2 to the 5 chirality operator, and it depending on eigenvalue of plus and minus eigenvalue of this chirality operator, you just decompose irreducible representation. Okay, so that's what we have learned, and this is Ramon, and then the last time I didn't explain properly about the NS vacuum. So I just said this is almost definition. So you have the unique vacuum ground state of the NS sector, whereas you have 32 states naively in Ramon sector. And since I just said it's fermionic. It's fermionic, but the fermionic means that the reason why you have fermionic is that you have a ghost vacuum. So ghost vacuum, as I mentioned, you have a BC ghost and you have downspin. Okay? You have to tensor. Indeed, this one is indeed incorporate this tensor. So this bosonic or like a matter vacuum times this fermionic vacuum BC coming from BC ghost. The reason why you get the fermionic is really the BC due to the BC ghost vacuum. And then we introduce so-called Gsr Projection Operator, which is equal to 1 plus minus 1 to the f over 2. And let's see. The problem of NS is indeed so a ghost and a matter is indeed equal to 1 over 16d. And if d is equal to 10, a total, this is NS. Oh, sorry, this is 0. Sorry, this is 0 for NS sector. NS sector, correct? Yeah, NS sector. NS sector is this one, and a total. So from here, a total is indeed minus 1/2. So you still have a tachyon in NS sector. That's the problem we have. But we will introduce so-called Gsr projection operator in NS sector, and you have to so which means that the state has to be more like a bosonic. So if you have negative sign for this minus 1 to the f, you have it's projected out. So at level 0 tachyon state 0 p GSO dk ns is projected out. So there's a projected at the projected. So that's so you can avoid indeed this minus 1 the tachyonic state due to Gsr projection. And then so the next so this is level 0, and level 1/2. Next you have to consider 1/2, which is the state which is created by e to the zeta psi minus 1/2. This is creation operator acts on NS sector. So this one is indeed polarization vector. And zeta can be understood as polarization vector. Here I'm going to talk about the open string, maybe or left holomorphic sector. If you want to consider cross string, you can just have anti-holomorphic sector corresponding. This is a polarization vector. Okay. And then I just call it this one is equal to zeta and and then if you use, so this has the, of course, as you can easily see, even, so this is Fermionic, Fermion minus 1, and this has minus 1. So in total, you have a plus 1. So it's included in the spectrum. And then you can just consider first the BRC quantization condition. This one is equal to m. So this is the positive mode acts on this zeta and k, which has to be 0. Is equal to due to the BRC quantization condition, or this is really an annihilation operator. So therefore, and if you use the computation relation between Gm and psi, one can obtain this is equal to alpha. Let me write down here k dot theta 0 k. So therefore, so the polarization vector has to be orthogonal to the momentum. So this means that if you have a K, so you can have the polarization vector theta has to be orthogonal. So it's the same as the massless gauge boson, as you can easily imagine. So this will create massless gauge boson. So we assume that this the level 1/2 this has we assume this is massless. So therefore L naught X. So this has the interpretation Hamiltonian and S include. So this one is alpha K square zeta K and S, and this has to be 0. So therefore this is massless. So we assume this is massless mode. Okay. So that the problem tachyon is avoided by Gsr projection. Next has to be massless. And then we impose BRC quantization condition, which is G matter minus 1/2. Yeah, so the BRC quantization condition will tell us that this NS mode, NS vacuum has to have 2 alpha, which is the, I think I made a mistake. This should be zeta. Sorry, I'm pretty sure this has to be. Why do I think this? Oh, no, it's okay. Sorry. It should be. So remember that the G matter is something like I think I'm getting rusty. Yeah. So G minus 1/2 of M is indeed sum over alpha n psi minus 1/2 n. Okay. Plus n minus n. Minus n, and then okay, so then this n grounds like this way, and since alpha zero, yeah. So since alpha 0 is essentially square root to alpha prime and p mu, right? That's what we already learned. Okay. Do you remember? So if you look at the n equals 0 part, this will give you k dot psi minus k 0 0 k, and then ns. Okay. So therefore, this is the indeed it has to be 0 to be a set. So therefore, this k zeta. So if zeta is proportional to k, it's unphysical. So that's what it means. So this zeta dot psi minus 1/2 is unphysical if the zeta is proportional to k. So this is exactly the condition for the vector bosons, massless boson. So therefore you have k squared is equal to 0 and k dot zeta equal to 0. So polarization vector has to orthogonal to the momenta, and also k mu is equivalent. Zeta mu is equivalent to zeta mu plus the shift of momentum. So this is physically equivalent. That comes from BRC quantization condition. Okay. So this is exactly the condition coming from NS. here, and then so therefore it looks like you have the 10 degrees of freedom, but once you impose this condition, you only have 8. So mu runs for 10. How to say? It's a 10-dimensional superstring, 10-dimensional. But once you impose this physical condition and massless condition, polarization has to be also a momenta, then it becomes representation. Representation SO8 acts on 8 and B. So it's called vector representation. Representation. So vector representation is very simple. So what is the definition of SO8? SO8 is 8 by 8 matrix. 8 by 8 matrix. MN. What was it? Okay, sorry. 8 R, and then we just impose A transpose A is equal to 1 and determinant A is equal to 1. Okay. That's the SO8. The vector representation, literally the matrix A acts on. So matrix A acts on A in the vector, like a B1 dot B8. So this is called vector representation. So it's 8-dimensional. Okay? That's a vector representation. And we will learn. So in Ramon sector, we have a spinor representation or conjugate spinor representation. What was conjugate spinor representation? Both 8 dimensions. And the reason why, one way to say the superstring has to be 10-dimensional is that we want to have little group has a special representation. SO8 is very special. So this SO8 is a little group of this one is little group of SO1,9. So it's a little group, and this little group has a very special representation. Vector and spinor and conjugate all have 8-dimensional. So that's not coincidence. So to have nice spectrum in superstring, so little group of the Lorentz symmetry has to have some special representation, and D equal 10 is really what's happening. D equal 10. D equal 10. Little group of SO8. SO8 has a very special property. That's why we have nice theory for superstring. Okay. And let me move. So let's take a look at how they appear from now. Okay, so in Ramon sector, so this is the Gsr projection for indeed NS sector, as I mentioned. So this is GX projection for NS sector. And then Ramon sector Gsr projection just pick up one of the irreducible representation. There are two choices. So there are two ways to define a GSO. I mean, it's up to your choice. It's up to your choice. You just have a parity transformation. You have two ways to define GSO projection. This is Ramon sector. There are two choices, and this 16 plus 16. So they differ. Okay, maybe let's write that this one. 32 is equal to 16 plus 16 prime. So they differ. The space-time parity transformation. So either you pick 16 or plus sign or minus sign, depends on your choice. which one is whichever is okay. Let me. Okay. Okay, so let's look at the, so as I mentioned, so you can just have a linear combination. So you have the, we define, so linear, you just consider linear combination of SK for Ramon. I define some, so this is can be understood as some polarization vector. I mean, it's just a linear combination of the spin up and down. And I define U dot K of Ramon, and then so BRC quantization condition will impose G0 and has to be 0. So this is coming from BRC, and that will give you square root alpha prime US, and you just use a computational relation between psi, this gamma plus, gamma plus, and the psi. And then what you get is K dot gamma S prime and S prime. I mean, I no longer write down the vector. Okay, maybe I just use the both ladder as I used. Okay. Again, so G0 is proportional to how to say alpha 0 and psi 0, right? Psi dot mu. Yeah. So it has a, it contains, G0 contains alpha 0, psi 0. That's the most relevant part. And the alpha 0 is essentially proportional to alpha. Did I don't have to, it should be 2 alpha in there. Oh, okay. I think psi 0 is normalized, I think, to yeah, so this gamma. So this is no correct normalization I took. So as I mentioned, psi will give you gamma matrix. Okay, gamma psi 0 mode of psi will gamma matrix. If you normalize this way, this alpha 0 will give you momentum, and the psi 0 will get gamma matrix. That's how you get it. And then this equals to 0 for BRC quantization will tell us that the K dot psi gamma and times US has to be 0. And this is indeed a Dirac equation. It's a momentum mode of Dirac equation. So it's massless Dirac equation. So essentially, I dot psi axon equivalent to this one. I think there are no gauge fields. I think I should use this one. So this is equivalent to Dirac equation. So momentum representation of Dirac equation. So it's Dirac equation, massless. Okay, so therefore, it's once you take K, so classically, so if once you take the light cone, K is K 0, 0. So then gamma plus. So this this equation will amounts to the let's see, gamma plus 0. U has to be 0. That's this master-spherical equation amounts to this U. So U is actually can be understood as some spinor. It's a Dirac. Okay, so then, so from here, you can just take the U it corresponds to plus or like a spin up S1, S2, S3, S4. Then it automatically satisfies. Okay, so again, so therefore once you specify the plus so once you specify the momenta, so it automatically specify this physical condition 16 is decomposed by 8b plus 8s plus 8b. Not B, sorry, C. So it automatically decomposes into the 16 representation. It depends on chirality operator, so it's even or odd. Okay. So 16 degeneracy will depend. So I think I should write down like this. So this is the even number of the plus sign. I think a minus sign. Sorry. So this one I call even number of downspin, and this is odd number of downspin. Okay. So they decompose into the two irreducible representation, depend on chirality operator. Now chirality operator is something like a you just avoid 0-1 direction. So psi 2 dot psi. That's a chirality operator that decomposes into two irreducible representation. Okay, so that's how we obtain the spectrum of the physical spectrum of Ramon Field. Okay, so this is the again representation of SO8, but no vector. Its dimension is the same. Dimension is the same, but their dimension is the same, but they are different representation. They are not isomorphic. It's a spinor representation. It's a spinor representation. This is spinor representation, whereas this is vector representation. And we will see how this Gsr projection will act on these operators, these states or representation of letter group. Okay, any questions so far? Yeah, I mean it's a conjugate spinor representation, so it's conjugate. So in the homework, I just give you the Dirac while and also Majorana condition. In addition to that, I just want the complex conjugation. There's a section, subsection for complex conjugation in the homework, and you see how they are related in the homework. Yeah, it's a conjugate spinor representation. So they are not they are different irreducible representation of SO8. Letter group. Okay, so let me move on to transportation part. function. Okay, so last time I talked about the torus partition function for sonic string, and you have a dedicated data function for sonic string. Sonic string from dedicated data function to the some power t is the, I think this week's homework is the first. This week, last week homework is just derive a dedicated data function. You guys more explicitly, that's homework. And now we have the parametric degrees of freedom. Parametric or superstring will give you so-called the Jacobi theta function. 1, 2, 3, 4. I mean, some of the theta function, Jacobi theta function is more like a trivial one. Yeah, there is no theta 1. Theta 1 is vanishes, but essentially, depending on the boundary condition you impose, you get the so-called Jacobi theta function. That is also a very nice motion form. That's what we are going to see. And also, they are related to Gsr projection and so on. And it's very interesting too. Okay, so that's we are going to see. Okay, let's take a look at it. Yeah, so the choice of this plus minus sign will give you like a type 2A, type 2B. So eventually, that's really the choice. So we will see. Okay. Okay, so first, I think I just swapped the order, so I don't think. Okay. So let's consider Firmware partition function. Let's consider psi z. So I call it ZF. So I only look at the holomorphic sector. So this is Z and S plus Z and S minus plus E to the. So it's some phase we will introduce in ZR and plus ZR minus. Okay. So remember that so we impose, so you have a tau, and then what I meant is the Z and something plus minus, and the R or an S is indeed trace of plus minus to the F, so E to the 2 pi I tau Hamiltonian NS, and then Ramon NS. So this is the definition of the partition function. So remember that so you have, if you have a partition function, the torus and 1 and tau, so you can define the partition function by just I didn't have top and bottom, but in Firmware you have to be careful of boundary condition. So if you have a non-trivial cycle, you have to specify boundary condition, either plus or minus. So I already forgot which way is which. Ramon, you have to be careful about the. So cylinder, I think. Let me be careful, precise. I think Ramon. Okay, I think Ramon, it should be periodic on a cylinder. Okay. So this is spatial. If it is periodic, corresponds to Ramon. Okay. Whereas anti-periodic, corresponds to Navier-Schwarz. Okay. And here I call it the time direction plus corresponds to anti-periodic. And minus corresponds to periodic. So remember that this is the boundary condition we will impose. Okay. So if you have a circle, you have to specify either periodic or anti-periodic boundary condition for Fermat. So this really minus really coming from this minus sign, -1 to the f. As I mentioned, if you impose this one, time direction has to be periodic. Whereas if you don't include this operator, you have to impose anti-periodic. That's indeed a usual boundary condition without inserting -1 to the f. And likewise, so we introduce Ramon and Navier-Schwarz because of the spatial periodic anti-periodic. Okay. So this is the condition, and you have to sum over all the boundary conditions to consider the Fermat partition function. And let's evaluate one by one. Okay, and then remember the H and S. So this is periodic in time circle. Periodic on time circle. Oh, and then H and S is L0 minus C over 24, and then here you have sum over R is the one top infinity R sum minus R sum R minus D is now 10. So 8 over 48 D minus 2. So which is what? Oh my goodness. It should be, sorry. Oh my goodness, what I'm doing. It should be 1 over 6, right? It should be 1 over 6. Anyway, let's say leave it. Ramon, you have a same, but this has to be infinity R equals to 1, R minus R equals R, plus 8 over 48. Okay, so that's the Hamiltonian we get, and we will do the same computation as the bosonic string. We just compute Fox space, Fermat Fox space. Okay. So okay, so then what we need to do is as follows. Let's see. Okay, so we have to sum over all the hero space. So here you have to sum over all the hero space, and we just take a look at how the hero space look like. So as I mentioned, so Ramon's sector vacuum has to be s.k without imposing Gsr projection, and the 32 state, and then the choice of S0, we depends on the 16 or 16 prime. Is it true? Did I say so? Let me check. No, I don't think so. I think I made some wrong explanation about the S0 choice will lead to 16 and 16 prime. It's not true. Okay, so we choose S0 is equal to up sign or up. Did I say so? Yeah, up sign due to Dirac equation and Dirac equation. Okay. And then so if you use the information -1 to the f acts on this s, so this is the you can just consider the definition -1 to the f, so -1 to s divided by 2. Anyway, so I think I just write down the following: I runs for 1 to the 4. 1/2 minus SI. This one is the correct. So this is the how the -1 to the f acts on. So therefore, if you have the sandwich by the vacuum, Ramon vacuum, the f, so then you have the following consists by 16 plus for plus sign, and then you just have zero otherwise for minus sign. Yeah. Am I correct? Sorry, I just got confused. Why is it minus sign? It should be 1, right? Sorry. It should be. Why is it minus sign? Can you see that? Why is it minus sign? So it should be 1, right? Plus minus 1. I think it's just typo. Yeah, it should be plus minus 1. Plus minus 1 depending on the choice of S0. Plus minus 1 choice of with the S0 is equal to plus minus. Sorry, this is typo. Because I mean, this -1 to the f will give you just some power. It doesn't change the state. So you can sandwich, you get 1. So this is just typo. Sorry. And then let's count the Hilbert space with this. So let's first look at the NS sector. The NS sector, you have a vacuum which is projected out by Gsr projection. But let's first consider without considering Gsr projection. And the NS sector, you just act. You have -1 to the whatever. Let's see. So you have. In this sector, you can just have a Fock space -1 psi -3/2 psi -5/2 and acting on vacuum. And here N1, N2, N3, and so on. And I is either 0 or 1 because of Firmware connection. That's how you create a Hilbert space. And then you just sandwich by this guy. So this is actually numbering operator. So this is numbering operator. So you just count how many, how to say, creation operator acts on how many. So therefore, essentially, what you get is as follows: trace. So for instance, Z and S plus is equal to trace of there is no minus sign to the 2 pi I H and S. Okay, and then this is minus 1 to the 1/2 is just give you Q to the 1 over minus 1 over 6. This is minus 1 over 6, right? And then, so this numbering operator will count how many times it acts on this one, which will give you 1 plus. And this plus sign, because there is no minus sign here, Q to the 1/2. Okay, so this is numbering operator that counts the level of this the creation operator. So this 1 plus Q 1/2 is if this one acts on the vacuum, you count Q to the 1/2. Otherwise 1. The same thing. 1 plus Q to the 3/2. Okay. Whether you just act this creation operator or not, you have count either 1 or plus Q to the 3/2, and so on. Q to the 5 over 2, and so on. Times. So this one you can just write down this one as the sorry. And you also have to incorporate this direction to the. It has the mu, okay? And one, it has these direction in space-time direction. And here, so if you impose physical condition, mu runs for whatever, 2 to 9, okay, 2 to 9, which is a little group, which is a little group direction. So therefore, everything have an 8. Okay. This runs for 2 to 9. So therefore, at the end of the day, what you get is a product of 1 plus Q to the 2n plus 1 divided by 2 times 8 and rounds for 0 to infinity. I think my lecture note is a bit different summation, but anyway, it's the same. So then this one is introduced by way before the string theory. It's introduced by Jacobi. It's 2, right? It's not 3, sorry. Tau over eta tau to the 4th. So that's the introduced by Jacobi in like the 19th century to study of some special function. Okay. So that's what you get. And do the same exercise for an S, but minus 1 to the F insertion. Minus 1 to the F, Q, and then Q to the H and S. Okay, so this one will give you as follows. Since okay, so you have to be careful about this plus minus sign. Depending on plus minus sign really come from depends on S plus R, S naught. Sorry, this is the Navier short, so you don't need to worry about plus minus sign. Sorry. What am I doing here? Sorry, so I don't understand. Sorry, Q to the 1 over 6. Minus, this is the same as here, 1 over 6. I don't know the plus minus sign, but you do the same exercise. Now you have minus sign included. 1/2. So if you include this, this minus 1 to the 1/2 sign acts on the vacuum, you pick minus sign and so on. So you just have minus sign here. The 8 minus to the 3/2 to the 8 and so on. this will give you Q3 minus 1 over 6 product of y minus Q3 to n plus 1 over 2 to the 8 and rounds for 0 to infinity. And this one, Jacobi call it this theta 4 tau over 8 tau to the 4th. That's the definition you can consider. And also, now you have considered z to the r plus, which is the trace of e to the 2 pi I, or q to the h Ramon. And now we just pick, there is no this is plus sign. Oh, okay, I see now I understand that this should be 0, I think. This should be 0, sorry. I need to take a, this is plus sign, you have a 16 degeneracy, and the q to the, sorry, this is 24. Okay, one third. Sorry. So this you have to be careful. You just take a look at the an part. You have to be careful. An part 1/3, and then now you have infinity. I mean, it's the same exercise. Now Ramon, you just act minus 1 mu and 1 minus 1 minus 2 acts on and 2 and so on to the vacuum. Okay, Ramon. Okay, so that's the how they act on Ramon vacuum. So now, if you act minus 1, you have 1 plus q to 8. And then if you act minus 2, you have 1 minus q squared to the 8. And so on. Okay. So that's how you obtain the partition function, and this one you will get minus 1 to the 16 q to 1/3 times 1 plus q to the n to the 8, n runs for 1 to infinity. And this one has to be equal to so Jacobi called this one is equal to a tau to the 4th. So Jacobi called it theta 2. Okay, and then next, to be honest, I don't understand why you get 0. Let me think why you get 0 here. Does anybody figure out that this has to be 0? It seems like it have to be have 0. Do you understand? Do you understand? Why do you have to be 0? Sorry, so this has to be periodic. Let me think why you get 0 for a moment. To be honest, I don't know. Let me think. Okay, so I don't understand why it has to be 0, to be honest. Okay, so let me move on. So let's let me. So this has to be 0, but I will answer after the break. Okay, so let's take a look at this one. So I just give you some example for modular transformation. Modular transformation of Jacobi theta R of tau. So as I mentioned, as we have seen, so you have so this one. So here you have so NS is theta 3 is corresponds to theta 3 corresponds to anti-periodic. Okay. So this is the Z and S plus. Okay. Yeah. And next you have periodic in time direction anti-periodic. So this is Z and S minus. Okay. And another thing what we have see is the periodic and the anti-periodic. Z Ramon and then plus. Okay. That corresponds to theta function 3, theta function what was that? 4, and theta function 3. Okay, and let's look at the modular transformation for these guys. And then as you can easily see, in modular transformation, S swap the spatial and the time direction. You swap spatial and time direction. Anti-periodic does not change anything. Therefore, it's invariant under S transformation. And if you do the T transformations just tilt this line to this line in diagonal. Okay. And the anti-periodic minus times minus will give you plus, right? So it becomes periodic if you do the T transformation. Therefore, if you do the T transformation, the partition function will modify to periodic. Therefore, theta 3 is indeed invariant on the S transformation by up to some factor. And this is, once you apply T transformation, theta 3 is transformed to theta 4. And then the similar thing one can do that even if you, let's see, so this is T transformation. And then if you swap the S transformation swap with spatial and time direction, so then they are related by S transformation. Okay. So A and P are swapped. So therefore, theta 4 and theta 2 are swapped by S transformation. And then so here you have T transformation. T transformation just change the, so minus times P is minus, right? Minus times plus is minus, still minus, okay? So therefore, anti-periodic becomes still anti-periodic if you do the T transformation. This is minus sign and this is plus sign can be considered. So therefore, minus times plus is still minus. So therefore, this is invariant T. And this is also invariant by T. Okay. So that's how it works. And if you look at the appendix, no, appendix. Next section, I have give you a definition of theta function. Theta function and its transformation under the S and T transformation, and this is compatible with the this physical consideration. Okay. That's the. So it's a bit early, but I want to figure out why you get 0. So let's take a break for a while. So let me think why you get 0. Why do I get to...
Professor?
Yes.
If you have time, can I ask you a question about the spin representation?
Okay.
Yes, so the question is in all dimensions, the gamma matrix's representation of the spin group is not a faithful group. It's not a faithful representation. So why we still call it spinors, and why we would like to consider
Odd dimension is not faithful.
is not faithful.
Why?
Because I mean in even dimensions you run from gamma 1 to gamma 2D, and these are faithful representation of the Clifford algebra and therefore the spin group. But in Augmentation, how you add new element, you just add the product of gamma 1 to gamma 2D.
It's just clarity operator. Okay.
Right, and then it's not a faithful representation of the Clifford algebra, because in the Clifford algebra, you multiply all the elements, you should not get identity here.
That's true.
Right. So while we, in that case, it seems in Automation,
but why it has to be faithful?
It may not be faithful, but I think if you want to get some I think spinor is something associated with the spin group, and if it's not a faithful representation, basically it's not just transforming under spin group. It's actually transforming like under some like a quotient subgroups, something like that.
Why does it have to be? Why does it have to be faithful? I don't understand what you mean. Why it has to be faithful?
Then what's the purpose of still considering gamma matrices for optimization and construct spin them that way? Is there any physical reason to that?
Why not?
I think it's just strange because I think the normal I think the Euro-physical motivation of using a spin group for Minkowski space is the spin group is a universal double cover of the Lorentz, right? But yeah, and so you can promote a projective representation to a non-projective one from the SO 3,1 to spin 3,1. But in other dimension or in other signature, the spin group may not be simply connected.
Why? Is it the case?
I think spin n is always simply connected, but for other signature and other dimension, like spin, I don't know. I think I saw this somewhere, like spin 3,3. Okay. So if it's
how do you define spin 3,3?
I mean, spin group is defined by the from the Clifford algebra. It's all elements in the Clifford algebra that on the intrinsic adjoint representation preserves the. You have like an element in the Clifford algebra, and you preserve the vector space. That's the definition of spin group, and it's always regardless of the space-time dimension, and signature is always double cover of the SO PQ, but sometimes it's not simply connected. Sometimes the gamma matrices representation are not faithful. I don't know why we would still stick to the gamma matrices in other dimension. If we are losing these, I think, naively nice or natural properties. That's that's what I'm wondering.
But that's different from your original question of optimization.
Yeah, it's basically two questions. The first, what's the physics motivation of using a spin group when it's not simply connected? The second question is, if you are using a spin group, but you are not using a faithful representation, so this is essentially, this is a bit strange.
Why? But you can always consider Fermi in odd dimension. It has to be representation spin group, even odd dimension, 3 dimension. Why not you cannot consider Fermi as odd dimension?
Right. It's a representation of this spin group, but not a faithful one, and I feel very strange. Is there a faithful linear representation of the spin group in odd dimension? And shall we call that spinor?
I don't know. Why not?
I don't know. I'm just asking.
No, you can just consider Fermi in odd dimension.
I can consider, but you have to, if you want to define like Fermi as spinors, and I'm just saying the definition as like Fermi as or spinor as something transforming on the gamma matrices. I'm not sure like if this is a very natural or very physical definition for me.
Why? Why not? For me, it's natural.
Because gamma matrices in different dimensions, they have, they're, I don't know. I think they do not carry the same physics meaning, or like mathematically they are related to the spin group in a different way.
Okay, I don't know.
Okay, never mind. Thank you.
I don't understand why I get zero. I don't understand why you get 0 here. Yeah. Why do I get 0? Let's see. I understand what's going on. Sorry. Okay, let's start. Yeah, sorry. Now I understand why you get 0. So the reason why I get due to presence of 0 mode. So as you can easily see, so here this is the operator, and if you insert -1 to the f, this is the. So therefore, if you have to sum over all the how to say Ramon vacuum. So if you have whatever S0 and S1 is plus and some S1 S2, S3, S4. So this will get to, this is +1/2, so therefore this -1 to the f is equal to, indeed, plus the same thing. And okay. However, if you consider minus sign, okay, minus sign, you're going to consider minus sign, okay. Sorry, I should have known that. So if you do negative, so if you do negative, you have a minus sign. You get the minus sign, right? So if you put this is because 1, so you have a minus sign. If you do SI is -1. So therefore, you always have a pair between plus or minus. Okay, do you understand what I mean? It's 4. Okay, and if you sandwich, you get a plus sign and minus sign, and you have to sum over it. So they cancel always. Do you understand what I mean? So if you sum, so -1 to the f, sorry. So if you insert -1 to the f, you always have the, how to say, upstream and downstream, they cancel each other. So therefore you get 0 sign, 0. Okay, good. So therefore, if you consider, let me erase here. If you have, so this is due to Firmware 0 mode. Sorry, I should have known that. Zr minus, I think Zr minus should be something 0 times q to the 1/3, and then minus sign, 1 minus q to the n, 8, n runs from 1 to infinity. So it should be 0. So that's how you get the 0 in the theta 1. Okay. So this is due to the Firmware 0 mode with the presence of 1 to the -1 to the f. Okay. So that therefore you don't need to consider this partition function. Okay. Good. Okay. So therefore, at the end of the day, so in the total partition function we consider is as follows. I think I shouldn't erase this one. And the sign. Okay, so the sign we will get. So here in the lecture note, I was in the plus minus sign I write down here. But so remember, -1 to the f to 0k of ns vacuum is indeed -1. So due to the ghost vacuum. Okay, therefore it should be minus. Okay. It should be minus. So it starts with 0k, and it just created the Firmware clock space. So therefore, it should start with -1. So this is minus. So therefore, at the end of the day, torus partition function ds of tau has to be equal to 1/8 and tau, and then you have some phase eta theta, and then theta 2 tau to the 4th plus tau to the fourth, minus theta, this is theta 4 of tau to the fourth. Okay, so that's how we get this minus sign really comes from the NS vacuum. And then, so if you use this modular property, okay, if you use this modular property, so this phase has to be fixed. So we want to have this SL2Z, PSL2Z, to the acts on this Firmware partition function ZF of tau. Okay. So we want to have this is, so therefore to fix, in order for the partition function to be modular invariant, indeed this sign has to be minus. Indeed, this sign for this one, for this has to be minus 1. And this is indeed so-called Jacobi identity. This is equal to 0. If you put minus 1, it's trivial. It becomes trivial. So this is the only way you can get the modular invariance. If it is 0, I mean modular action is trivial. And then so minus 1 theta 2 to the fourth plus theta 3 to the fourth minus theta 4 to the fourth is equal to 0. This is for Jacobi identity. So Jacobi has found this identity in 19th century, but from by considering the string theory, you can naturally reproduce what Jacobi ingenuity of Jacobi by just considering naturally appear. And let's consider what it means indeed. So indeed, so how you get this one? So this combination can be written as follows. So this combination can be written as follows. Indeed, what we have is this CF can be written of tau can be written in terms of as follows: 2 times trace of 1 plus minus 1 to the f over 2, and then sector Hilbert space q to the h and s. And then you have the minus sign 2 times trace of 1 plus minus 1 to the f over 2 e q to the h Ramon. And this one can be understood as Gsr projection operator of the Firmware. P Gsr. This is Ramon. This is an S. So here, even if you put the either plus minus depending on sign of S naught, okay? This is depending on sign of S naught. But due to the presence of Firmware 0 mode, it doesn't contribute. So the partition function itself can be written in terms of Gsr projection. Okay, so then, so here, so that due to the presence of this one, you can just get rid of the tachyon mode, and here you get the physical partition function. So physical partition, this one, this combination, if you put the minus sign, this combination can be written as the physical partition function. Okay, so let's move on to the type 2 string. So type 2 string, So in cross strings, we just need to consider the vacuum of the cross string. So you just first consider massless mode of this one, of the superstring, and then type 2A and type 2B indeed is the choice of the Gsr projection, left moving and right moving. So as I mentioned, you have NS vacuum. So NS vacuum tachyonic. So then massless state becomes 8V. Okay. For Ramon, you have two choices, 8S, depending on the Gsr projection, plus minus sign. Depending on plus minus sign. So you have two choices. C. Okay. So then you can just have the two choices you can make for massless spectrum. So right moving mode is 8S, whereas you can take the opposite chirality for 8B plus 8C and 8B plus 8S, and then type 2B is the same chirality. It's a choice you can make. So this is the same chirality for type B and the opposite chirality. Opposite chirality. So the opposite means the spinor or conjugate spin. Okay. OSO8. And then, of course, you can have other choice, but they are parity invariant. Parity redefinition. And then you can just do the following exercise. So it's a representation. So everything representation boils under representation of a little group SO8. So you have 8V cross 8V is indeed decomposed 1 plus irreduced representation of the 35. Okay. So do you remember how it decomposed 8V? This is familiar decomposition. Do you know what it is? What 1 corresponds to? What 28 corresponds to? Good. So this is an anti-symmetric. Symmetric. This is symmetric and traceless. And this is trace part. Okay. And this indeed happened in the. It's the same decomposition for bosonic string. You have B field and then the graviton. It's the same as bosonic string. And then you can have Ramon. So this is NS sector. This, of course, here NS sector. Here NS sector, and this Ramon sector, NS sector, and Ramon sector. In Ramon sector, we have the 8S times 8C in type 2B, type 2A, and this will decompose by 8B plus 56T. People just denote. So this can be understood as 1 plus 3. 3. 1 plus 3. So 1 plus 3 means that it's just anti-symmetric representation. So this n is n times anti-symmetric representation. And people just usually use this one is the C. It's a vector. It's Ramon Field. It's called Ramon Field. So it's everything anti-symmetric. So if you swap n and m, you get a minus sign and so on. On the other hand, you have on the other hand, for type B, so type B, you have the same chirality, 8B cross, 8S cross 8S, which is the 1 plus, it's very similar to upstairs, 28, but it's a different content. 35 plus, and this 35 is not the same as that one. This is 0 plus 2 plus 4 plus. So this is the some scalar C, and the antisymmetric tensor. Second antisymmetric is the force, but this plus means this. But this is self-dual. This plus means self-dual. Okay, self-duality. Self-duality means that if you take, let's see. So it's 10 dimensions. So self-dual means that if you define this C4, right? C4 plus, and take D is equal to star D C4 plus. That's what it means. Star. It's a hot star. So if you define H M N P Q as a just a, how to say? They just act, the external derivative acts on N M Q Q R M N P Q R. Self-dual means that you just consider epsilon tensor, whatever. It's 10 indices. It's kind of tedious to write down, but that's n1 dot n0 dot 9, and h n0 dot n4 should be equal to h n5 dot n9. Okay, that's self-dual means. Understand? That's self-duality. And this is called this C is usually called Ramon Field, and Ramon Field, and this will lead so-called coupled to D-brane. D-brane. We will see it immediately. D-branes. Okay. So if you have the point particle, the electron moving along, so this is coupled to mu. Okay, this current is coupled to mu, right? And the gauge field, it's electron. But if you have extended objects that can couple to some other, like higher form gauge field, you can consider this Ramon field can be understood Ramon higher form gauge field. Okay? So we will see. So the difference between, so here, what was that? Type 2A, you have only so. Type 2A, you have odd, okay? Odd number of indices, whereas here you have an even number of indices. That will give you the difference between what kind of DP brane you can have. Okay, and then you can. So have Ramon and NS, Ramon and SNS, so we can just consider so you can just consider the following So you can just consider the following. So the NS and Ramon, in that case, and Ramon NS. So in that case, here, so 2A's Ramon NS or NS, Ramon NS and NS Ramon. Okay. So essentially what we need to consider is also same here. Ramon NS and NS Ramon. Okay. Essentially what we need to consider is this one, 8B cross 8C, which is equal to 8S plus 56C, and 8B cross 8S is equal to 8C plus 56C. Oh, sorry, S. It's a different representation. Okay, and then this one is usually called Gaussian. This one is called Gaussian lambda plus. Sorry, it's not Gaussian, Dilatino. Sorry, I'm sorry. So it's a super partner. Am I correct? Yeah, super partner of this one, Dilaton. Dilaton field, Dilatino, and also here you should have the psi minus n. So this 56 is indeed super part. So this is Gravitino. So this is called Dilatino, and then lambda minus and psi plus. This one is psi plus. So we just use the notation. This is called Gravitino. This positive chiral, negative chiral. So it should have the, as you can easily see, so this has the chirality m, and so vector coming from vectors and spinor chirality. Okay. Spinor chirality. Whereas here you only have a spinor. Indices. Okay. So this is Dilatino. Okay, so that's how we obtained the spectrum, mass spectrum of type 2 and type 2b theory. Okay. And then I just written down the table in the lecture note how this spectrum look like. And if you count the bosonic, so here you have a bosonic degrees of freedom. Okay, bosonic degrees, whereas you have here is fermic degrees of freedom. And it's supersymmetry. Supersymmetry requires the number of bosonic mode and fermic mode should be the same. Let's do that. So here you have 8 times 8 is 64 massless state. And here also you have a mass 64 massless state. Okay. So from NS you get the bosonic massless state. From Ramon you have a 64 massless state. Whereas again you can see this is 64 massless fermionic state. From NS Ramon and Ramon to NS you have a 64 massless fermionic state. So they are super partner to each other. That's a typical feature of supersymmetry. So you have the same degrees of number of freedom of the massless bosonic and fermionic states. Okay, so that's we have the spectrum. And now, so let's look at this Ramon. So let's focus on this Ramon part. And as I mentioned, these are coupled to the some So D-brane. So as I mentioned, so this Ramon, this flux or whatever, Ramon flux is just a flux. It's usually people just write down this. So 2A, you have C1 and C3, and type 2B, you have C0, C2, and C4 self-tail. And you can just consider Ramon flux means you just take the external derivative. You have H2 form, you have the C1, and also you have H4, which is the C3, and so on. H1 is equal to HC0 and H2, H3 is equal to DC4, DC2, and then H4 is also H5 is self-tail. Okay. Self-tail. Okay, that's what. And then, so as we know, in the QED, so if you have an electron that interact with the gauge field, electron has zero-dimensional object. Okay. The electron is zero-dimensional object that move around in the time direction. We will have the same thing. Indeed, this H2, so type 2A, so you have the so-called DP. Okay, type 2A, you have DP, P brane, and then P is equal to odd or even. Which one? Do you know? Type 2. Odd or even? Type 2A. Type 2A, this is even. And then, so the reason why is that you have a two form, right? Sorry. The two form that is coupled to two form D0 brane. Yeah, sorry. So this so D0 brane coupled to the one-dimensional object. Yeah, or one-dimensional form. Okay. So D0 is really like a point particle that coupled to one-dimensional one form, right? So here it's electron is zero-dimensional object that coupled to one form. Okay, coupled to one form. So therefore D0 brane coupled to one form. One form whose flux is two form. Okay, so it's electromagnetic field is F mu nu. It's a two form. Okay. So the D0 brane coupled to the C1 form, and C3 is D2 brane. Okay, D2 brane. And if you can take magnetic dual. Okay, if you take a magnetic dual, it becomes the magnetic dual D4 brane coupled to the magnetic dual of this flux, and also magnetic dual of the 0 is the 46 brane. Will couple to the magnetic dual of this one, like that way. And then type 2B, the P brane, P has to be odd. So there is so-called instanton. D minus 1 plane. Actually, D minus 1 plane coupled to D0 form. D minus 1, the P is a spatial direction. Okay, spatial. So therefore, D minus 1 means you just pop up at the. So this is time direction, and it somehow pop up at some point in time direction and it disappear. Okay, that's D minus 1. So that's called instanton. That will give you instantaneously appear in one point of time direction and disappear. That's why it is instanton. Coupled to this one, and D1 brane coupled to two form, and D your favorite D3 brain. DC brain come to self-deal 4 form. The reason why you get, I told you your favorite D3 brains, if you apply n DC brain and take large n limit, you get it is 5 process 2 S4 S5. So here, on D3 brain, it's a space dimension three-dimensional and the time direction 1-dimensional. So it's 3. The wall volume we get 3 plus 1 dimensional. Okay, 3 plus 1 dimensional, and then on which is 40 angle 4, so-called supersymmetric ambient theory lives on. If you take large n limit, you get it is 5 cross S5. Okay, so therefore type 2 it is CFT corresponds to really come from type 2B string theory. Okay. So if you got confused about how P even or P odd, you just always think about where does the CFT come from. So I mean, the most famous prototypical example comes from DC brain. So type 2B. Okay. So they couple each other. So that's what we're going to learn. Okay, still have time. Okay. So before that, but let me introduce the D brain more primitive way. And so on. D5, so as I mentioned, so D type 2A, as I mentioned, D0 brain, D2, and D4, and D6 are magnetic field. I hope I'm not mistaken. So they are magnetic field. So they are magnetic electromagnetic field. So this is EM field, duality. And that couple of this C1, and then C3. Whereas in type 2B, what you get is type 2B, you have D minus 1 brain, D1 brain, and D3 brain, and D5, and D7. They are magnetic field, where it's a soft field. So therefore, it's either can be electric or magnetic object. Okay. Self field. That's why you have C0 and C2 and C4 and plus. Okay, that's how we get. And we will see. How it appears. This is the again EM duality, electromagnetic duality. Okay. So before going that, so this is the extended object. So in type 2 thing is D equal to 10. So it's extended object. So DP brain is a stack of D brain. Okay, so let's call a stack of DP brain. It's spatially stack of DP brain. So let's go stack of DP brain. P is a spatial. So P is the spatial. P is the dimension of spatial direction. Spatial direction. And you always have the time direction. Okay, you always have time direction. So essentially, this has space-time direction p plus 1 dimension. And then this extended object on which the open string can end. Okay? Open string can end, as you might have heard. Open string can end. So for type 2 string, as I mentioned, you have how to say holomorphic and anti-holomorphic. You have 8 cross 8, essentially S or V and so on, S and V or C and so on. Everything cross string. We just consider cross string spectrum. We all consider here is cross string spectrum. However, once you incorporate the D-brane, one can once you introduce the D-brane, one can incorporate even open string. So without D-brane, it's just a cross string. But with D-brane, you can just incorporate open string. Open string can. And then, so it's a boundary condition. So therefore, so if you consider so y is called D. D comes from Dirichlet, as you know. So this is the spatial direction. For instance, xi. So let's consider. So this is spatial direction xi, and then the other direction is the xa. Okay. And this is, let's see, time direction. Let's consider this is time direction. So this time direction, let's see, time direction x0. So then A runs for 1 to P, 1 to P. And this is time direction. So this is P plus 1 dimensional object. And xi, the position of xi has to be fixed. So this is Dirichlet condition. Xi has to be fixed. I runs for P plus 1, dot, 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 3 minus 1. Okay, so this is Dirichlet condition. Let's go. Dirichlet. Whereas for open string, you have a Neumann. Neumann means the partial derivative on E is equal to 0. So this is the Neumann. A runs for A runs for 1 to P. Yeah, 0 to. So this is a Neumann. Neumann boundary condition. So that's the simple boundary condition one can take. Okay. It's a very simple thing. One can just do that. Furthermore, oh my goodness, I think furthermore, so as I mentioned in the previous time, so one can do the following thing. So one can do the following thing. So for instance, if you have stack of, let's see, stack of, so I just look at this direction. Look at stack of D-brane. So this is D-brane. So you have n D-brane. So let's n D-brane. N D-brane. So you can have, let's call 1, 2, 3, 4, dot, 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 n. You can open string can end on like, for instance, one can end on like the same brane, or you can just end on some other brane. Okay, some other brane. And this degrees of freedom is called Champeron degrees of freedom. Champeron degrees of freedom. Degrees of freedom. So one has to incorporate that exactly will give you non-abelian gauge field. So for open string, so as I mentioned, open string you can just have Firmware space. So you have some vacuum, either NS or Ramon, and you just act on some only holomorphic or anti-holomorphic, depends on brane or anti-brane, some N1, anyway. 1, alpha 2, mu, and so on, and also parametric states can act on this one. So that's all. That's how you get the open string spectrum. Minus 3 over 2. It's if it is ns. If it is ns. Okay? That's how you get, and you get the numbering. So that's I call it numbering operator with momentum k. With momentum k, but one can also incorporate these degrees of freedom. So when which brane it can end on. So therefore, this one is incorporated nk, and furthermore, you just can consider I and j. I and j means the starting point is i's brane, and the ending point is j's brane. So that's called Champeron degrees of freedom. So this one is called Champeron degrees of freedom, I and j. And this is indeed the same as we just incorporate the gauge boson. So gauge boson, so here, so massless gauge boson is, as I mentioned, in the mu, and that acts on k. So that's for ns, right? So that's massless gauge boson appearing from ns sector. Okay, that's what we have learned. But so by incorporating I and j degrees of freedom, this becomes non-abelian gauge field. Gauge field. So in other words, so this where it ends depends on where it ends. This a mu takes the matrix value. So a11, a12, mu. So it's a21, mu, and so on. Okay, a and n and mu, which can be understood as mu a ta. Okay, and ta is the basis of un the algebra. So this ij can be understood as the ijth element of this matrix. Okay, so that's the that's called Champeron degrees of freedom. Moreover, one can do that. So lots of things one can do. I mean, it gives you dynamics of the gauge field, and then so in standard model, so you have the abelian gauge field or non-abelian gauge field, depending on the energy scale you will look at. For instance, so you have the SU3 plus SU2 standard model plus U1 gauge field in standard model. Okay, and this is called the strong force, whatever color, and people just call maybe people call E and Y. I think these are hyper U1, SU2 is weak, so maybe W, Okay, that's people call it, and this is non-abelian. So these are really non-abelian gauge degrees of freedom. So if you have number of stack on brane, so here only at this moment you can have a UN, but later we introduce called oriented fall. Oriented fall you can just realize SP or SO gauge group even. That I will introduce later. But from here, so we already knew that if you do this, so there's a Higgs mechanism. Higgs mechanism that breaks down to the U1 electromagnetism to this SU2 cross U1. So once you have the web of Higgs field to be some field, becomes W boson, Z boson become massive. Okay, massive. And if you go to the low energy scale, lower than the mass of W and Z boson, you have electromagnet, only U1. Okay, a medium gauge field. And you can do the same thing for even using D brane. Even if so, if you have the stack of D brane, you have a massless, massless field, massless open string. But if you move the D brane to a little further more, you can have the mass of gauge boson proportional to the length between D brane. Okay, that will give you the massive gauge boson, or not massive gauge boson. So that here you have U4 gauge group, but you have a U1 gauge group. And if it is previous, you have the only 5 U5. Okay. U5, it just moves one of the D brane to the right. To the right, you can have U5. It breaks down to U5 is broken to the U4 times U1. So this is indeed a Higgs mechanism. You can Higgs mechanism. So here the gauge boson become massive, and then the gauge group is broken to U5 times to U4 times U1. This is exactly the similar phenomenon for standard model. Okay, so by Higgsing, so this is a massive gauge boson. So let's look at the bit more detail about this type 2 string. I already given almost answer. So let's keep it this one here, and then let's move on to the. This is very important. Okay, so just recall that the so you can have if you have electron with a source, so electron can be, so you have electron coupled to gauge field. So it can be understood as the action can be understood mu, J mu, is the force, x, and the electric charge is here. That's the action of how they interact with each other. And this can be understood as so this can be understood as the word line of C and mu dx. So this word line of so given the electron, so this word line of the electron coupled to gauge field. So similarly, so dp, so S of dp action can be understood as the word volume of dp plus 1 and coupled to cp plus 1. Therefore, as I mentioned here, if if you have a D0 brane, it's a point. It's like a point particle moving along the time direction. Can couple to this one form. And then similarly, if you have D2 brane, you can couple to the Warburg symmetry couple to D3 brane. And then furthermore, if you have magnetic monopole, if you have magnetic monopole, so magnetic monopole, let's call the M. You can have magnetic flux along. You have magnetic flux, and then so you just have the, how to say, it's dual. How did I explain? So this I call it S. I shouldn't use S indeed. Let's call sigma of F mu nu dx mu. So this x mu nu is magnetic flux. Is quantized as which can be understood as so the ball. Oh, sorry. I think yeah. So the ball written here inside of this is, let's call B2. B2. It should be B3. Okay. B divided by df divided by Stokes by Stokes. And we do the same here. So if you consider the D brane, you have a magnetic charge can be understood, Qm can be understood as the ball of D. So we can still have draw the similar figure. So I can do the same thing. So so given the D brane, so D brane is here. So this dp brane, and then consider in the space-time dimension D dimensional, and then consider the sphere around here. So then, so this is dp plus 1 object, so p plus 1 object, and then so therefore this sphere can be understood d minus p plus, what was the answer? So this is dp, right? P plus 1. So therefore, so let's do the similar exercise. So this is 0-dimensional object, and 3-dimension is this d minus 0 minus 1. 3-dimension. So therefore, here it should be d p plus 1, like this way. No, 3. This is 3-dimensional. Am I correct? I think, yeah, this is correct. D minus 1 is spatial direction. So this D minus 1, 1, right? Okay, D minus 1, 1. And its spatial dimension is D minus 1. And then D minus 1, and it's 0-dimensional. Am I correct? Okay, so let's do step by step. Okay, so it's codimension, D minus P plus 1 is codimension, right? And then take codimension 2 surface, D plus 1, and codimension 2 surface. Okay? So this sphere has a dimension like this way. So therefore, this has to be D minus P minus 3. So this surface is D minus P minus surface. Therefore, it should be this sigma, corresponding sigma is D minus P minus 3 surface. which is integrate out the this G. G is equal to, how do I define G? Yeah, so this H. Hopefully what I'm doing is correct. Let's do the same thing. So dp brane HP plus 2, and then star H. It should be star H. You can just flux the star H, and this can be understood as the sum of the ball. Seems like I made a mistake. Why that? Okay, I see, I understand. Sorry, I think I made a mistake. It should be D minus 1. I got confused. Sorry, how do you do that? In D, how do you do that? It should be D minus P according to. Sorry. Okay, let's do step by step. So you have a DP brane, electric DP brane, that coupled to, as I mentioned, that coupled to DP brane. Okay, DP brane that coupled to CP plus 1. And take the deal, take the extended derivative, you have HP plus 1, okay, P plus 2, which is DCP plus 1. And take magnetic deal, star HP plus 1. Star HP plus is indeed D minus, D minus P plus 2. Okay? D minus P plus 2. Okay? So therefore it should be D minus, this has to be D minus. Okay. Sorry, my calculation is wrong here. Okay, and then, so you just take the, so this star H can be understood as D times C tilde. And the C tilde is indeed D minus P plus 3. Okay, so now everything okay. And that is coupled to magnetic deal of D minus P plus 4. Right. That coupled to. So that's electromagnetic field, EM field. Okay, so therefore this then what I did is correct. Sorry, what I did is totally correct. Okay, so then here you have D minus P plus 1 in the ball, and this one is integrated out with the which form? D star H. Okay, so that's okay. So that's what we have. And then relation between D0, D2, and D4 and D6 are written here. Okay. So there are magnetic deal. Yeah, once you put the, you start with D0 brane, it should be 10 minus 4 is D6. and that coupled to C1, and they're related by this relation. Okay. So, yeah. And I just want to make one remark about the type 2 string. Oh yeah, so then I want to make some one remark. One remark is that so this B field is coupled. So if you look at this B field, so B field, so you can just consider similar thing, B2. Okay. You can have a B2 in type 2 string. So this one is indeed coupled to some object. So this B field, this is B mu, is coupled to like go F1, just fundamental string. So as I mentioned, so these two form, Ramon 2 form coupled D1 brain. Okay. However, this is an anti-symmetric tensor. Okay, and a similar thing you can see in the B field. Okay, so that this two form is coupled to string. Indeed, open string, and you can do the similar exercise to do you can just take the 3, 4 and the magnetic dual and they come back. Okay. If you do that, you can have the dual of this object. So that's called NS5 ring. So as you can see, D1 is magnetic dual to D5 ring. Okay. So therefore, F1 is dual to NS, so-called NS5 ring, electromagnetic dual. So you do the same exercise. So you start with B2 and take the H3, which is equal to dB2, and take electromagnetic dual, which is Hodge star, okay, which is the 7th form. And if you take, you get this B tilde 6. That coupled to NS5 ring, NS5 ring. Okay, so that's what's going to happen. And then this NS5 ring always exists, even type 2A and type 2B. So in addition to Ramon is from Neville-Schwartz. You can have this NS5 ring and F1 string. And also here, you can have NS5 ring and F1 string. F1 is just an open string or fundamental string. Okay, and as you can easily see, here you just go. I'm not going to. I will tell you later. Type 2B, so-called S-duality. Type 2B, it has so-called S-duality. S-duality D3. So S-duality is leave the D3 brain as it is S-dual, but the fundamental string is S-dual to D1 brain. And then NS5 ring is dual to D5 ring, S-dual, by S-duality. So you can just swap F1 and D1 by so-called S-duality. So there is a so-called, and this S-duality is really the S-duality of for the negative fourth theory. So that's what we're going to learn later. So yeah. So this there is some duality that swap fundamental 3 and D1, and so NS5 and D5. And furthermore, we will see here, so non-dynamical object called D8 brane. D8 brane. You can incorporate D8 brane, which is the non-dynamical. Later, we will, so far we just consider type 2 series, but later we will consider so-called heterotic string. Heterotic string, you can have heterotic string. You have some left moving string. Left. It depends which convention I took. It's either left moving is bosonic and right moving is fermionic. It's very strange. That's why it's called heterotic. I took, yeah, bosonic. Left moving is bosonic. So left moving, it should have 26 dimension, but right moving is fermionic. So in this series, you can only have NS5 and F1 string. Okay? F1 string. You cannot incorporate D brane. But furthermore, so-called there's the M theory, which leads to so-called heterotic M theory. It's D equal 10, but we will see. So if you go to some strong coupling limit of the strong coupling limit, it becomes heterotic M theory, which introduce so-called M9 brane with which is D equal to 11. And if you go to the type 2A description, I will explain this M9 brane becomes D8, non-dynamic object D8 brane, and everything related to so-called duality and so on. And you can also incorporate so-called oriented fold. Or all plane. So that's what we will learn, all plane. And we will just introduce all plane in type 2B, and the so-called oriented fold projection. What you end up with is the 2A theory, the type 2-1 theory, that leaves like a D1, D5, and also another D9 brane will show up. Space filling D9 brane will show up. Okay, so that's what we are going to learn from now. It's going to be a bit more interesting instead of just doing the worksheet analysis. So this D brane will give you some dynamic, really non-perturbative dynamic object phenomena in superstrings. Okay, and then, so I don't think I have time to do that. So next we will learn T-duality. So T-duality is the once in compactified on circle, they are related. Type 2A and type 2B are related to so-called T-duality. T-duality, and then so for instance, D2 brane can become sometimes D1 depending on the direction. D2 brane can be sometimes become D3 under T-duality. So that's what we're going to learn. So we put the theory type 2 theory on S1, but the radius R here, but there is radius 1 over R. So the R is the opposite. Then the theories are related to A and to B are the same once you compactify on S1 R and S1 1 over R. That's what we're going to see. Okay, so sorry about today's lecture. Sometimes I just didn't have so much preparation today. And we will take a look at T20 next time. Okay, let's finish.